So for the next topic, we're going to look at velocity and acceleration. And this is going to link the derivative to those physical concepts. And this is something that you already know, I think, quite well. So this is going to be very intuitive. So let's assume we have an object that moves along a straight line. So for instance, moves along the x-axis. And this object could be anything. It could be a train that's moving along a track, or a car on a road, or it could be a ball bouncing up and down, just something that moves along a straight line. And we denote the position of the object by x as a function of t time. And here, so x is the position and t is time. And just to be on the clear side, we can say that we denote time in seconds or in hours if you want to, and the position in meters. We have our x-axis right here, and then we have a particle or something with position x of t. And what we want to know is we want to figure out, well, what is the velocity of that object? What is the acceleration, if there is any? And so on. And derivatives are going to give us the answer to that. So let's start with the velocity, and let's define concept that you know if you've been in a car or a train, the average velocity. So the average velocity of an object in over the time interval t plus h is the change in distance divided by the change in time. So you can write this down in mathematical notation. V average, AVG, is delta x, that's the change in distance, divided by delta t, that's the change in time. And we can make that more explicit because here we speak about the time interval t to t plus h, so it's x at t plus h minus x of t divided by h. And you can already see the expression for a derivative coming in here, and that's not a coincidence. And just to firm things up a little bit, an example with real numbers. If you take the KTX from Seoul to Busan, you know that the distance delta x is, roughly speaking, 350 kilometers. The delta t, so the time needed to travel by KTX from Seoul to Busan, is about 2 hours. So you know that the average speed of the train is the distance covered divided by the time that it took to do that. So 350 divided by 2 kilometers per hour, which is 175 kilometers per hour. And it's important to keep in mind that this is an average distance, an average velocity. So the instantaneous velocity will change quite a bit, In the beginning, the train will speed up, and then when it hits a nice smooth track with no villages or cities around, it will go very fast, and then it'll slow down again to reach the city. So the velocity changes, but on average, the velocity is 175 kilometers per hour. So now that we have the average velocity, we can also talk about the instantaneous velocity, and that is the velocity at a given point in time. And in order to define that, what we're going to do is take the average velocity, but make the time interval smaller and smaller. So in other words, if you compare with the definition on the previous page, what we're going to do is let h, the length of that interval, go to 0. So what does that give us? It gives us the velocity v as a function of time t, and it's given by the limit for h going to 0 of the average velocity. And so we can be a bit more specific. This is also the limit of h going to 0 of x t plus h minus xt divided by h. And so what do we see? Well, here we have the expression for the derivative. So this is a derivative. And what we end up computing here is basically, in other words, d dx, so d dt of x, the derivative of the position x. There's also a special notation for the rate of change with respect to time. There we use the following notation. We say that Vt is x dot of t. But you can also write it as x prime or as dx dt and so on. So this is called x dot. We only use this notation if the derivative is with respect to time, but you see that quite a lot in physics textbooks. And now a couple things to note, so maybe more convention than anything else, but there are a couple of special cases. So if the velocity is bigger than 0, then what we have is that x of t is increasing and our object is moving to the right. So we basically have our line here, our x of t here, and then the velocity being positive means the particle or the train or the car moves to the right. And the opposite is also true. If it's smaller than 0, then x of t is decreasing, moving to the left. And then the last case is v of t equal to 0. And here you have to be a bit careful. V of t equal to 0 means that the velocity is 0 at one specific point t. So we say that x of t is instantaneously at rest. So instantaneously means at that time. Doesn't mean that the particle is at rest all the time, just at that specific notion, at that specific time. And then one last remark, we can also define the speed of a particle or an object, and the speed s of t is just the absolute value of the velocity. So what this does is it ignores the sign. So let's look at a quick example of all of these concepts in action. So let's say we have a ball is thrown in the air. And we assume that that happens vertically. So I'm standing here and I'm throwing this ball into the air like so, just straight up. And so it's still a one-dimensional motion. It's not horizontal like a train or a car, but that's fine. Vertical is also okay as long as it's along a straight line. And so what do we know about our ball that's thrown in the air? We know that it has a height h of t given by the following expression, 4.9 times t minus 4.9 t squared. So we denote the height of the ball at any time. We denote that by h of t. So now the question is, find the velocity. Well, that part is easy. We just have to take the derivative. We get 4.9 minus 2 times 4.9 t is 4.9 minus 9.8 t. And then secondly, very straightforward, find points where v of t is bigger than 0, less than 0, and equal to 0, and interpret them. So we see from the above expression that v of t is equal to 0 if t is equal to 1/2. So if you put 1/2 in there, you get 4.9, and we are back to 0. And then it's also easy to see that v of t is bigger than 0 for t less than 1/2, and v of t is smaller than 0 for t bigger than 1/2. And now for the interpretation, well, this is easy to see if we go back to our physical example. We know if we throw a ball into the air, the ball is going to go up and it's going to slow down until it reaches a maximum, and then it's going to be attracted to the earth again, and it's going to fall and eventually hit the ground or keep going. So we know it goes up, and then here it stops, and then here it goes down again. And now we can put some numbers on that. So it goes up for t less than 1/2 second, and then at t 1/2 second it reaches the maximum point, and then for t bigger the velocity is negative, so it goes back down. And we can study that a little bit more if we graph the various quantities. So I'm going to draw two graphs. On the first, I will put h of t as a function of time. And so what I have for h of t is that this is a nice parabola. And in particular, it has zeros equal to 0 and 1. And then the function h of t is equal to, like it has this graph. and then it continues like this here. But we're mostly interested in what happens between t0 and 1. And so what can we derive from this graph? Well, we see as t increases, the height of the ball increases until it reaches a maximum here at t is equal to 1/2, and then the ball starts getting attracted to the earth again, and it goes down and it hits the ground at t equal to 1. And if there's nothing stopping the ball, then of course it continues past t is 1 and the height becomes negative. But let's just assume that it falls on the ground and it stops there. And likewise, we can graph the velocity, so v as a function of t. And here the zeros of the function are 1/2, and the intercept of the function is 4.9. So the drawing is not really to scale on the axes, but we see that the velocity is a straight line like this. And in particular, what do we see? Well, the velocity is positive for t less than 1/2, so that's here. And then the velocity is 0 for t equal to 1/2, and the velocity is negative afterwards. V of t less than 0 for t bigger than 1/2. So now that we know about the velocity, let's also talk about the acceleration. And that is very similar to the velocity. So we already defined the velocity as the rate of change of the position. And now the acceleration, which we'll denote by a of t, is the rate of change of the velocity. And we can equivalently write this as, well, it's the derivative with respect to t of the velocity. That itself is the derivative of the position, so this is the second order derivative of the position. And there's many notations. We can write this as x prime prime of t, but we can also write this with the dot notation as x dot dot. The important thing here is that we have the second order derivative of the position. So there's a couple of special cases to look into. So if a of t is bigger than 0, then we have that v of t is increasing. And likewise, if the acceleration is negative, then v of t, the velocity, decreases. An important caveat. V of t increasing does not necessarily mean that the particle is speeding up. And likewise, the velocity decreasing does not mean that the particle is necessarily slowing down. And to understand why that is the case, we'll think about a particle x of t with negative velocity. So here v of t is negative. So the particle itself moves to the left. And here, if a of t is positive, then what that means is that the acceleration counteracts the velocity. It makes the velocity increase. The velocity is negative, however, so in magnitude the velocity becomes smaller, and what the particle actually ends up doing is the particle slows down. And then for the acceleration negative, you can have a similar example. So here, if we have a particle that is moving in the negative direction, again, v of t smaller than 0, so it's moving to the left. Now, if a of t is also negative, then what that means is the velocity and the acceleration work together, and a of t causes the velocity to become more and more negative. So the particle here speeds up, but it goes in the negative x direction and moves to the left. What you have to do in order to figure out is the particle slowing down or speeding up, you have to consider both of these at the same time. And what you can do is you can say the particle will be speeding up if the velocity times the acceleration is bigger than 0, and slowing down if the velocity times the acceleration is negative. So let's do an example. So for this example, we have particle P moves along the x-axis with position given by xt is equal to 2 times t cubed minus 15 times t squared plus 24 times t. And let's compute a couple of properties. So first, find v of t and a of t, the velocity and the acceleration. So for that we need to compute the derivative, and we get 6 times t squared minus 30 times t plus 24 for the velocity, and for the acceleration we have 12t minus 30. And now some physical properties. In which direction is P moving at t is equal to 2, question mark, and is it speeding up or is it slowing down? So in order to answer that question, we take our velocity and we plug in the value t is equal to 2. So we get 6 times 4 minus 30 times 2 plus 24, which is minus 12. So that tells us that on our line here, if this is x t equals to 2, the velocity is negative, so the particle is moving to the left. Is it speeding up or is it slowing down? Well, for that we need to compute the acceleration as well. And the acceleration is 12 times 2 minus 30, which is minus 6. The acceleration has the same sign of the velocity, so the acceleration points in the negative direction. So we can conclude that the particle is speeding up. So we take the product, get minus 12 times minus 6 is 72, which is positive, so speeding up and moving to the left. So then, moving on from that, when is P instantaneously at rest? And when does its velocity instantaneously not change? So the key word here is instantaneously. That means at specific moments in time. So for the first part, we have to look for zeros of v of t. So v of t is 0 if 6t minus 30t plus 24 is equal to 0. And I will let you solve that quadratic equation yourself, but you should get that t is equal to 1 or t is equal to 4. And then for the second part, we have to look at the acceleration. So where is the acceleration equal to 0? So that means 12t minus 30 is equal to 0. And this is easy to see. For that, t is equal to 30 divided by 12 or 5 divided by 2. And then a couple of global questions. So for the last part, when is the particle, when is P moving to the left, and when is it moving to the right? So for that, we have to look at the velocity as a function of time. And what we can do is we can use a sign chart. So we already know that there are some specific values where the particle is at rest. So t is 1 and 4. And so here we have that the velocity is 0. And then we know for t bigger than 4, the velocity is positive. For t in between 1 and 4, it's negative, and t less than 1, it's positive again. So you can get these signs by just plugging in a value and seeing what the sign is. We don't care about the actual value, we just care about the sign. So now from the sign, you see for t less than 1, the particle is moving to the right. For t between 1 and 4, it's moving to the left. And for t bigger than 4, it's moving to the right again. And we can try to draw that very imperfectly, but basically what we have is that our particle moves to the right like this, and then at t equal to 1, it stops, and then it starts moving to the left again, and at t equal to 4 it stops again and it turns and it continues on to the right. So it goes like this, and then like that. And the last question, when is P speeding up or slowing down? And for that we have to combine the signs of the velocity and the acceleration. Now we have three values to take into account. So we have 1, 5/2, and 4. So these make the velocity 0. This one makes the acceleration 0. And we know that the signs are plus, minus, 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 plus. And then for the acceleration, we have minus, 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 plus, plus, plus. And now if we compare each in turn, what we see is that at t equals to 0, the particle is at rest, sorry, t equals to 1, and likewise, t equals 4, the particle is instantaneously at rest. And then below t is equal to 1, the velocity is positive, so it's moving to the right, but it's slowing down because the acceleration is in the opposite direction. So it's going to the right and it's slowing down. And then between t1 and t5/2, the particle is going to the left because the velocity is negative. And the acceleration is also negative, so it's speeding up. And then here, the particle is still going to the left between t5/2 and 4. But now it is slowing down. And then finally, for t bigger than 4, the particle is moving to the right and is speeding up. And you can again try to visualize that on the trajectory of the particle. You sort of have, well, the particle comes in from the left and it moves to the right, and it's initially quite fast, but then it has to slow down because again at t equal to 1 it has to stop and start moving in the opposite direction. And then it accelerates, but then it has to slow down again because it has to take another turn and go back, so that deceleration and turning back happens at t equals to 4. And at t equals to 4, it basically starts speeding up and then it goes very fast and basically goes off to infinity even.